Hello, stats class. Here is lesson 13.1b, which is about calculations for ANOVA. So I told you yesterday that we would learn how to do the calculations today, and we're going to start by talking about the test statistic, which is new. We have not seen this one before. It is called F, named after Fisher, who was one of the big statisticians who invented things. So the Fisher F test is what it's called. And it is calculated as we talked about the good variation and the bad variation. We're going to learn how to estimate or how to calculate those today. Divided by the bad variation. So the more good we have compared to bad, or the bigger F is, the more likely we are to reject. Another way of looking at that is, remember, the good variation is the differences between groups. And the bad variation is the differences within. So today I'll show you how those are calculated. So before we talk about how they're calculated, let's talk about the distribution of F, because it's a weird distribution. It actually looks similar to chi-squared on a graph because it's always skewed right. And just to visualize, it's still skewed like that. How skewed depends on the degrees of freedom, and that's kind of like chi-squared also. So it could be like not so skewed if df is larger, or if df is smaller, it could be really, really skewed like that. Lots of different possibilities there. This would be a larger df. This would be a smaller df. But then it's even more complicated because there's two different types of df in this chapter. That's kind of crazy. There's a degree of freedom for the numerator of our fraction, which is a good variation. And there's a different one for the denominator. So I'm going to show you how to calculate both of those. They're not very hard, actually. That's the easy part of the calculations. So the numerator, df, is, we're going to call it df1, is the number of groups minus 1. And remember, we can have as many groups as we want. Usually there's 3 or more. And that, especially the number of groups, is called k, so that's k minus 1. So let's say we have our sample size, n1 and n2 and n3 and all the way up to nk, and however many of those there are, we subtract 1. Okay? These are the sample sizes of the groups, and we're going to use them to find the other df. So the denominator df, df2, is the total sample size minus the number of groups. I'll write it in words first. Minus, I didn't leave room for that number of groups. And so we already know that the number of groups is called k. The total sample size is called n, capital N, which is the sum of n1 plus n2 plus all the way up to nk. Or you could write it with sum notation if you wanted to. The sum of all the n's is capital N, and so that means that df2, I'm going to put it down here because I didn't leave space. Come on, df2 is officially capital N minus k. So those are the two things you need to know for df. Before we go on to the slightly harder part, let's do an example of that with the warm-up information. Remember, there were 4 fertilizers being applied to flowers, and we had 3 groups of flowers that were all 8. So N1 and N2 and N3 were all 8 flowers in each group, and then remember the monkey got the last one, so N4 was only 7. That was kind of entertaining. So capital N would be 8 plus 8 plus 8 plus 7, which comes out to 31. There's 4 groups here. 1, 2, 3, 4. So this is k equals 4. And then if I wanted to find my df, df1 would be just the 4 minus the 1, which is 3. And df2 would be the capital N minus k, which in other words is 31 minus 4, which is 27. So if you think about the lists of data, we have these lists of data over here, and each list, this has 8 in it, 8 and 8 and 7. And what we're doing really is we're taking 1 off of each list. Leave off 1 from each list, and that gets you df2. So the total sample size is 31, all of these put together, and then leave off 1 of each, and you have 27. We're just trying to make it so it kind of makes sense to you a little bit of what we're doing here. And then, after you know your df's, you have to be able to calculate your numerator and denominator. So we'll talk about the numerator first. The good variation. Also called MSG, which stands for mean square for groups, because it's the differences between the groups. Okay, so what you do for that is you have to look at the means of each sample and compare them to the overall mean. So we've got x1 bar and x2 bar and all the way up to however many we have, xk bar are the means of each sample. And we want to know how far off those are from the overall mean. If you put them all together into one big sample, instead of 4 separate ones, or however many there are, you can be able to find the overall mean, which is just called x bar. It is the sum of all the values in all the samples divided by the big N, which is the sample size for all of them. So we're just combining them into one big thing. And the big x bar for all of them, overall mean, is calculated as, well, how do you find the sum of all the values? Well, x1 bar came from the sum of that one divided by n1. So if you undivide it, or in other words, if you multiply it by n1, you get your sum for that sample, and then you can get your sum for the second sample from n to x2 bar, and you do that for all of them, and then you divide by n. Or the way the book likes to write it is with the sum symbol, all of the ni's times xi bar over n, and I just represent whichever one you're talking about. So I starts at 1 and then goes to 2 and then goes to 3 all the way up to k. And that is not MSG yet, but that's okay. Then what you do is you take all of these x bars and subtract the mean and square it, and we've seen that sort of calculation before where we find the squares of something and add them up. MSG, or the numerator of our fraction, is the sum of all the n's times xi bar minus x bar squared over df1. Okay, that's a mess. It's not as bad as you think, but it's still messy. I'm going to do an example of this, but I think I'm going to talk about the denominator first and then come back to the example. So, let's talk about the denominator. Bad variation. So like I said, good variation is measuring how far from the mean of everything is each sample mean. We want them all to be close together, right? We want with good variation, or we want them to be far. We want to prove that they're far apart. I was wrong. We don't want them to be close together. We want them to be far apart. So with good variation, bigger is better. Bad variation is called MSE, and E stands for errors, or how far off something is from what we want it to be. Errors reminds me of residuals. It's kind of like residuals, except in a totally different context. So I'm just going to go straight to the Mfe formula. I don't have to do any introduction to that. It is the sum of, you do ni's minus 1. I don't have a good reason for that, I'm sorry. times the standard deviation of each group squared, and divide by DFT. SI is standard deviation of each sample. Because again, we're measuring the variation within each group now, and that's how we measure the good variation and the bad variation based on how far the means are from the overall mean compared to how much variation there is within each group. And then when you put it all together, you get your test statistic. Now I have some good news for you. Usually computers do this calculation for us. I'm going to make you do it by hand for one lesson. So today's homework for lesson 13-1B is going to make you do this by hand a few times. And then we'll switch to how do you read the computer output. Because I think it's good for your brain to have to do a little bit of extra algebra. MSG divided by MSE, which means it's kind of a messy formula when you write it all out, but I kind of like it anyway. You do NI, SI, bar, minus X bar. When I do the example, I think this will make more sense. Divided by EF1, which happens to be K minus 1. So it's a division over a division, which is the messy part. And then on the bottom you have the Ni minus 1 times the Xi squared divided by N minus K. So this whole thing is our test statistic. And then you can find a p-value, which is actually easier than you think because your calculator has a thing on it called FCDF. Isn't that convenient that they have that on the calculator? I mean, go look for it. It's in the same menu as normal CDF and T-CDF and chi-square CDF. It's there. And so you put your F value, and it's always a right-tailed test, but chi-squared. So you have F and then 999 or some big number. And then you have to have both DFs, DF1 and DF2. And so that's the easy part, and I'm not going to spend time worrying about it, although I will do it in my example. So the rest of these notes are an example of doing this with actual numbers, because I feel like you need to see that. I suppose you don't have to write this piece down if you don't want to, if you want to just watch, but don't just stop watching, because this might actually help you, especially help you get the homework figured out. So let's go back to the fertilizers. And I looked up, I actually typed in data in my calculator, and I found out the means. And so I'm going to write them down so that we have them off to the side here. In fact, I really should have called it, instead of 1, 2, 3, 4, I should have called it N, and P, and B, and this doesn't really matter. The first one was nitrogen, 15.625, and 13.5, and 14.625, and 13.286. I'm just writing this, copying this from where I wrote it down before. S2, S3, we also have to have the S's. So standard deviation of each one, I actually gave you those in the warm-up. They were 1.69 and 1.41 and 1.30. Actually, it came out to 302, and then the computer rounded it to 1.3 and 2.06. Okay, so we're going to use those numbers to calculate. Actually, I'm going to start by calculating the overall X bar. Overall X bar. Remember that our N's were 8887. I'm not going to write those down again, but the sample sizes were 8887. We already found the DFs, so that will help. So we have to do 8 times the 15.625 plus 8 times the 13.5. Let's see, this is a minute. That's okay. 8 times 14.625. Do this, even though it's not good notation. 7 times 13.286, and we're going to divide all of that by the total of all the n's, which remember we calculated up here, it was 31. 8 plus 8 plus 8 plus 7 on the bottom, capital N is 31. And if you do all of that, messiness, or if you take the data and just put it all into one big list and find the mean, you get 451 out of 31, which is 14.548 And I'm not going to show you that on the calculator. I'm just going to let you trust me. You can try it if you don't believe it. All right, so then from that, we can calculate SS. Actually, no, we're not going to do SS. I left off a detail this year, and I think it's better that way. MSG. The SS is just the top half of MS, if you really want to know. It's this piece right here, but you don't have to worry about it. So on the top of our big fraction, make a big fraction. On the top of our big fraction, we're going to do what it says here. We're going to do the n times the mean for that sample minus the overall mean squared. There's 4 of them. Let's see if I can fit them on the top of this fraction since I made it longer than that one. So we're going to put 8 times, you have to do the 15.625 minus the 14.548. It's going to be difficult to fit in, but that's okay. And then we're going to do it again with the second one, which is 13.5 minus 14.548. At least there's only 4 of them, right? The third one is also 8 minus 14.548 squared, and then the fourth one is 7, because there were only 7 plants in that last group because of the monkeys. 13.286 minus 14.548. It was difficult to fit that, and I'm not sure if that was the best idea. But anyway, we do all of that on top. Technically, that top part is called SSG, so don't need to worry about that. On the bottom, we put our DF, which was, as you remember from up above, it was 3. It was 4 minus 1 because there's 4 groups. Minus 1 is 3. And when you do all of that, I'm going to simplify it and go with that. So you get the top comes out to 29.26, and the bottom is 3, and you get 9.75. What in the world does that mean? Well, it's a measure of the good variation. It's a measure of how far off these individual means are from the overall mean. And you don't need to worry about the details beyond that. MSE is the bottom of my fraction. And again, it's going to be this big, long fraction until I simplify it, but that's okay. We're going to do, this time we're using n minus 1. So instead of 8, 8, 8, 7, I'm going to do 7, 7, 7, and 6. I might as well write that first. These are the sample sizes minus 1. And then the thing that I multiply them by is the standard deviation squared. So 1.69 squared, this one gets better, and 1.41 squared, and 1.3 squared, and 2.06 squared. So this is measuring the bad variation, or the variation within each group. On the bottom, I do GF2, which we calculated up here as 31 minus 4, which was 27. On the bottom, I have 27. And so the bottom comes out somewhere around 71.17. I think I may have used more digits when I calculated this, so if you're doing this on your own to see if I'm right, it might come out slightly different, but that's okay. And this is 2.64, and that is a measure of the bad variation. So the good variation is more than the bad. That's a good sign. It's not just about whether it's more, it's about the F distribution. F is, I'm going to write it with the fractions within fractions first, because I've often seen it written that way in books. So it's this, and then it's the 9.75 over 2.64, and then when you calculate that, it is 3.69. That is my test statistic. Take a deep breath. That's kind of a lot of calculating. I will not make you do it with 10 populations or anything weird like that. It's going to be 3 or 4 because otherwise it's just mean. But in your homework, you will have to do this at least once. I think it's twice. And then the p-value. We take our handy-dandy calculator and we look up FCDF. And we put in the 3.69, something large. DF1 is 3. DF2 is 27. And the calculator magically spits out a p-value, which is 0.024. And then, of course, you already know how to do step 4. We'll come back to step 4 tomorrow, or in the next lesson, 13.1c. But step 4 would be look at this p-value. It's less than 5%. We would reject the null. We would write a beautiful sentence about it. Right now, we're not worrying about the sentence. We're just looking at, can you do the calculations? Calculations are kind of a pain in this chapter, which is why 13.1c, I'm going to show you the computer output method. So there we go. That's plenty long enough for these notes, and we're going to stop there.